Welcome to a course on security threats in Wi-Fi wireless networks. This module will examine and present some specific instances of threats. A typical wireless network threat is related to the risk of establishing unauthorized connection to a shared medium. As an administrator of a wireless network, you can't control access to the network. Any person who is within the reception range of an access point may be an active user in a given network. As we've said, this is simply a matter of antenna size. Since anyone can connect to a network without authorization, it follows that anyone can eavesdrop on data transmitted in the network. What's more, attackers can intercept the data of other users who share an access point. This is much like working in a broadcast network with hubs and switches. Another typical threat is impersonating a trusted user. Computers are authenticated in Wi-Fi networks against their MAC addresses. A MAC address is not encrypted. It is transmitted in clear text using radio waves. To add to that, all network cards support changing their MAC addresses. The risk of deploying a denial-of-service attack that will block an access point hasn't been a problem for wired networks, or at least not to this degree. Since the medium is a radio wave, it can be interfered or jammed. Either of the two can be enough to disrupt the operation of a possibly important enterprise infrastructure. With wireless networks, you can run your own access point and spoof a trusted AP that was earlier used by clients. A client computer will connect to an access point that produces the strongest signal. We're back to the antenna size rule. If your rogue access point will have a bigger antenna, it will be used to establish connections with the network's users. Let's look more closely into this issue. You should be aware of the possible threats that await you if you use an unknown Wi-Fi network, especially if they're public. The attack I'll describe now was terrifically popular with intruders at European and US airports several years ago. From a technology standpoint, this attack is not a feat of creativity. It made use of a combination of simple technological solutions and basic social engineering tricks. A would-be attacker launches a fake access point in a crowded place, for example, in an airport terminal. To make users connect to this AP, the attacker's network has a legitimate-looking name, for example, Free Wi-Fi Airport or Heathrow Airport. Any innocent name will do. It could be the name of an internet service provider that is popular in a given area. The attacker aimed to scoop as many connections as possible. To achieve this, the rogue access points did not perform user authentication. They didn't encrypt transmitted data either. The networks were open. When you connect to an access point in an airport, a coffee bar, or a restaurant, you do it to gain internet access. That's why fake access points offered internet access. Any computer that connected to an attacker's access point sent data through the attacker's device. Even if an access point connection doesn't allow for changing some client-side network configurations, many configurations are performed automatically through an active DHCP. Let's move away from the risks connected with the possibility that it's an attacker who set a DNS server used by clients and take a look at a simpler matter. Users fully expect that once an access point connection is established and a website is opening, a page will be displayed from the Wi-Fi provider with a thank you message and a request to submit credit card details. As a result of this expectation, users will freely, in a transparent and unsecured way, provide the attacker with their credit card numbers. They send it to the attacker's server. If this trick is to be pulled off, a fake website has to look trustworthy. It should look similar to other pages from legitimate internet providers. There's a ton of tools on the internet that can help you download an entire web page to your computer's local disk. You can also download a logging page. It's not a problem anymore to set up a page that looks identical to any other page. I'd highly recommend to be cautious with using free public Wi-Fi networks, especially if a logging window appears with a request to submit any sensitive data, especially credit card details. This idea for attacks was subsequently developed and improved on. The next attacks targeted client computers. An attacker aims to intercept user credentials and use them to control a computer. We're back in a familiar scenario. A user is connected to a Wi-Fi network. An access point that supports the network is controlled by an attacker. The AP, which is at the same time a DHCP server, will then set up a default gateway, a router, and a DNS server. It doesn't configure a proxy server, an intermediary. The key objective of the attacker is now to force a victim's computer to send all data through his device, for example, a proxy server. If this is achieved, the attacker would be able to eavesdrop and modify the data sent by the victim on the fly. The on-the-fly modification of received and sent transmissions is a huge threat to computer security. We'll soon learn exactly why. An effective attack requires only to turn on the DNS server that was set for client computers by an access point as the default DNS server. The server has to be configured to return the IP address of your proxy server as an answer to all queries about names. Once it's configured, you control the communications channel between a client and the requested website. You can modify sent data on the fly. In the simplest scenario, you can inject scripts into data exchanged between the browser and the website. You can embed links to an invisible pixel stored on your computer disk on these sites. Displaying a page will also cause the browser to display the pixel. To download it, the browser will have to connect to your computer. While establishing a remote connection in Windows, before a logging page is displayed, the system sends user credentials to a given computer, probably using the NTLM protocol. Over the next module, we'll see that receiving an NTLM challenge is equivalent with obtaining a user's password. Inserting the above code line into a website means that the user will connect to the server number 10.0.0.1 and his credentials will be automatically sent there. The sent data won't authenticate the user and display the image, but we're quite satisfied with the information we've obtained. We've received a sent challenge message. Gaining control over a channel means that a person who set up an access point, for example at an airport or at a restaurant, knows our Windows password. This attack is still extremely popular and a number of variations exist depending on the prime target of the attacker. Attackers can attempt to steal our credentials to a given website. Instead of an image, an attacker can inject a script that launches an app or a code that is stored on his server. This code can be used, for example, to sniff out values submitted in login and password fields. A relatively recent, extremely vicious type of attack enables attackers to modify the data downloaded by users on the fly. If you connect to a web server using HTTP to download the file is not protected in any way. The authenticity of HTTP packets is not being verified. The packets are not encrypted. They can easily be modified by attackers on the fly. Fortunately, there aren't yet any openly available tools on the internet that make these operations possible. It's obvious that before you launch a program, a warning will be prompted. Do you want to run this program? It comes from the internet and is potentially unsafe. Because we've grown used to messages like this, we will automatically hit yes. As proof of concept, an attack consisting of a downloaded and modified file being digitally signed on the fly with a valid certificate was shown. A user was still prompted with a warning, but the window had a different frame color in Windows systems, and additionally, it came with the information that the file was from a trusted source. As far as client attacks are concerned, as you've seen, an attacker aims to convince users to connect to his fake access point. This can be achieved by setting up an access point that would establish connections to networks with an SSID that a user wants to connect to. The access point will listen to packets checking access points near the client. Then it will extract SSIDs and set up a network with a given SSID. This is another proof that turning off SSID broadcasting is not a good idea. A better solution would have an access point broadcast itself, and it would be up to the client to choose the appropriate connection. Despite all these threats to security, the advantages of wireless LANs outweighs the risks. What can be done to tighten up the security? There's only one solution. If you connect to an untrusted network, don't log into any important services, like your business mailbox or your bank account. Immediately after establishing an internet connection, configure a secure VPN connection to an enterprise server. You need to make sure that all communications are really sent through the VPN channel. This doesn't always have to be the case. It's a matter of varying levels of routing detail. A person who controls a fake access point could have predicted that we'll connect using a VPN and set specific points in such a way that will connect to some websites directly through the rogue access point. Evil twin attack is an interesting variant of client attack. The attack targets business VLAN clients. Attackers have to set up an access point with an SSID that is expected from a user. The rogue access point has to emit a signal that's greater in strength than the legitimate access points. A user knows that enterprise networks are protected and that he'll have to log in to connect. That's why a rogue access point will also employ a logging mechanism. A radius server verifies user credentials in business networks. Our access point will also be a radius server client, but unlike a legitimate radius server, the evil server will authenticate all users regardless of submitted logins and passwords. This means that users will always connect to our access points. Whether or not they will be granted internet access depends on our access point configurations and our subsequent agenda. Until we physically connect our access point to a business network, users will not be able to access the network. The damage, however, is already done. A user sent his credentials to an attacker freely. He had to do it because a radius server client, the access point, had to send it to the server. The data will either be sent in clear text or as a challenge and response message depending on a radius configuration. If the PAP protocol was used, the data will be transmitted in clear text. Because an attacker is not trying to make his own life more difficult, he'll set his rogue access point and radius server to use PAP. Radius clients negotiate different authentication levels from a list configured by an administrator. If a user agrees to use PAP, it's very simple from then on. If he doesn't, and goes on to negotiate a higher level authentication protocol, for example MS-CHAP, the challenge and response message will be encrypted with the user password. The encryption will have to be reversed. This operation will take us about 15 seconds. At this point, an attacker has obtained the user credentials. If he manages to physically connect to an enterprise network, he can, for example, log in as the victim. The fact that a user is connected to an access point means that the attacker is fully able to control a client. In this scenario, we did not expect any need for major user activity. A client was only expected to connect to an access point. What are the countermeasures? As a rule, you shouldn't only prove your identity to an access point. The access point should also prove its identity to you by way of mutual authentication. This would help prevent impersonating a trusted access point. Mutual authentication can easily be configured in Windows systems locally or using group rules. You can see the latter configuration below. You can select in EAP settings whether you want to ensure the identities of an access point or radius server. If it's checked, select Next, a certificate to be used for verification. A radius server is required to present its valid certificate that matches a certificate issued by a public certification authority. A common error in managing enterprise networks is failing to require mutual authentication. Another problem is accepting all the certificates pre-installed in a Windows system. This means that to run an attack, a potential intruder will only need to buy a valid certificate, which costs about $100. You should only trust certificates that were issued by your certification authority. You also need to have your own public key infrastructure. A denial of service attack is another matter. What is the easiest method for blocking out a Wi-Fi network? It's removing a magnetron from a microwave oven. After dismantling a microwave, you will find the device pictured above. It's the heart of the microwave. The magnetron shown in the picture is ready for sale on a Chinese website. This option works for people who don't want to dismantle their microwaves. It's enough to plug the device in and move away quickly. All wireless networks within hundreds of meters will be shut down. Easy and effective. What are the protection measures with regard to infrastructure attacks? All in all, given the outlined attack cases, you need to remember about several key points. Don't use the WEP protocol and try not to use the first version of WPA. If you are using WPA, or better still WPA2, this doesn't eliminate all potential threats. If you don't have a radius server, ensuring that your pre-shared key cannot be cracked is vital. The key shouldn't be found in any dictionary that would make you a prime target for known types of cracking. The key also has to be relatively long. The longer it is, the longer it would take an attacker to brute force it. Attacks can be automated using professional tools like Wireless Security Auditor, developed by Elcomsoft, a Russian company that specializes in cracking tools of all sorts. We've already talked about PSK attacks. We'll see an example of this attack soon. Summing up these two modules, I can risk saying that efficient Wi-Fi protection is relatively easy to implement. A good solution is authenticating users through the 802.11x standard, for example, radius server, and protecting transmitted data using the 802.11i standard, for example, WPA2. Let's see what could happen if we don't implement these recommendations. Our access points use the old WEP protocol or the first version WPA. Moreover, they operate in the pre-shared key, PSK mode, and don't use a radius server authentication. This means that we're ripe for simple computer network attacks. The programs that facilitate these attacks have been the basic component of the backtrack distribution for many releases now. The usage of these tools has recently become even easier. Previously, you had to type in about 4 commands in a command line, a terminal. If your operation required turning the interface off and starting it in listening mode, this took 6 instructions in total. Now, breaking into a badly configured VLAN is as easy as launching Fern Wi-Fi Cracker. The tool is planned to be a component of the newest backtrack. This is a small application with an intuitive interface. There's even an update button for checking the current version. It'll help us break into a weakly protected wireless network. I'd like to show you how this is done. The program is probably already available for Windows systems. We'll use its Linux version though because Wi-Fi card drivers that run on Windows don't allow active data exchange with networks you're not yet connected to. The basic scenario of some of the attacks is forcing a client to disconnect. We'll talk about it more during the demonstration. We'll start with switching to backtrack. Here's Fern Wi-Fi Cracker installed, configured, and running. This tool uses the AirCrack and AeroDump NG suite of tools. Other than these two dependencies, we'll also need running Python scripts. To launch an attack, we need to select an interface, a network card. The interface here is called VLAN1. After selecting the interface, you can select channels that are to be scanned by double-clicking anywhere in the main window. The tool is set to scan all channels by default. We'll want to scan for the access points with active connections instead. After clicking on Toolbox Settings, you can enable the feature that locates the output as geographical coordinates. You can also set the Wi-Fi attack options there. If MAC addresses are filtered, you can type here the MAC address that had been intercepted earlier, or submit any MAC address if you don't want your real address to be saved in the access point administrator's logs. Let's start this scan. Note that 2 monitors appeared. Fern Wi-Fi Cracker scans for networks protected with WEP in the first window, while in the second, the search applies to VLANs protected with WPA. Let's start with the WEP scan. You can see here the BSS ID of an access point. This is simply the physical MAC address of the AP. We need it for checking whether there's any active connections to an access point. The tool has detected one web-protected network, which means that looking at a MAC address, we know that it's connected to the found network. There are no other networks around. We've managed to detect a weakly protected network that is actively used at the moment. At the bottom of the window, you can see the number of the Ethernet frames sent and received by a client. We'll need now to choose from the main window the option you can see below. We need to select an identifier of the targeted network. In our case, this is default. You can select one of 3 listed attacks on web networks that can be seen below. You can also use default options and click on Attack. Since we've selected ARP Request Replay as the attack, we have an opportunity to see the communications between our computer and an access point. The point is obtaining a sufficient number of initialization vectors. If we manage to do this, we'll try cracking the key. Data encrypted with the same RC4 protocol key always looks the same. As you can see, we found out that an attack that consists of forcing an access point to generate initialization packets by responding to our ARP requests has managed to gather an appropriate number of packets. To be able to crack the key, we needed 29,362 packets in total. After gathering and saving the packets to pickup, both monitors close. At the bottom of the above window, you can see a hexadecimal value of the key. This key will enable us to connect to an access point, to a weakly protected web-encrypted wireless LAN. The whole attack took less than 2 minutes. While configuring a web-protected access point, you can submit a password in 2 formats, either in a hexadecimal notation or as an ASCII string. The attack we've run produced the first format output. If you don't want to use this format, you can convert it to ASCII code. We've connected an online converter. It's a converter we've been redirected to by a search engine. After typing in the key cracked by Fern Wi-Fi Cracker, it turns out that the password of the web-protected network is HackM. Now let's try to break into a WPA network. We'll start with detecting available access points. To do this, click on the listening icon again. 2 monitors pop up. We've seen them already. This time, we're not interested in web networks since we already know the key to the detected network. We'll focus on WPA networks this time. The program has detected 2 such networks. One of the networks is actively used at the moment. The BSSID of the first network is DD_WRT, and AD is the value of the end of its MAC address. We compare it against the end of the address that can be seen at the bottom. They match. We can conclude that the first network is the one being actively used. The next step is to click on an icon you can see below in the main window. We'll select the DDWRT network in the new window. Breaking into a WPA-protected VLAN amounts to cracking a pre-shared key. In the case of WEP, which is constantly vulnerable to attacks, even a good configuration of all settings doesn't mitigate the risks. With WPA networks, the attack is based on the assumption that the key will be easy to crack, and that it can be found on a word list of a given language. As you can see, we have 2 such word lists prepared. One is shorter, the other is longer. For the purposes of this presentation, we'll start with the short list. Everything has been configured. It's enough now to click on Attack. The attack can be apparent in this case. If a network user is really using it actively, for example, downloading large files, there's a possibility that our actions will disconnect and reconnect him to the network. He'll experience a connection drop. As Wi-Fi users, we're used to a connection disappearing sometimes and that it can become weaker or slower. In this case, we're trying to force a user to re-authenticate. We'll check each time whether the password submitted by the user can be found on our shortlist. As it turns out, it can. The password for the attack network is password. The 2 presentations provided examples of typical infrastructure attacks, breaking into Wi-Fi networks. You were able to see for yourself that protecting Wi-Fi is up to you entirely. Appropriate countermeasures can simply be not using WEP, and in the case you're already using WPA, deploying a second version of the protocol along with implementing strong passwords. The best solution is to authenticate users through a Radius server. Thank you.